risk assessment.
Thanks, Mark. Good morning, everybody. Like Mark said, I'm going to be talking about strength and breakup factors in asteroid impact risk assessment. Anyone who's been following the impact scenario, this conference knows by now we have this probabilistic asteroid impact risk model that uses fast-running analytic and semi-analytic models to evaluate the probabilistic risk of asteroid impacts. And the idea behind these kind of models, the simplified models, is not so much to accurately predict every single impact for very specific cases, but to get a sense of the trends and sensitivities given a large degree of uncertainty across the problem. So one of the areas that has a lot of uncertainty remaining are strength and breakup factors. What are the properties of the asteroids, how those properties make it interact in the atmosphere as it comes along, where that's going to make it airburst, and then how that energy is propagated to the ground to make damage. So we're going to look at, in this talk, some examples of where those sensitivities are and how they can sort of interact to make some counterintuitive trends that can sort of lead our intuition astray. None of these factors are particularly novel in and of themselves, but the way they interact can sort of be counterintuitive. So in our risk model, we use the fragment cloud model to integrate the entry and breakup of our asteroids. It integrates the single body standard meteoritics equations for the entry and uses a combination of discrete fragmentation and aggregate debris clouds to sort of represent the breakup process. And from that, we get an energy deposition curve of the entry and breakup. And from that, we can estimate an airburst altitude or an effective airburst altitude. And one of the advantages of this model is that it's both very fast running and efficient, but it also can produce a variety of energy deposition curves. And these can represent both the uncertainty in the breakup process and different breakup characteristics that could arise from asteroids of different structures or properties. So these plots show an example of some energy deposition curve variations given different initial strengths, strength scaling coefficients for the fragment, the successive breakup, or different aggregate cloud fractions. So once we have an airburst altitude from our entry model, the next step of the process is to estimate the damage on the ground. One common way of doing this is to use height of burst maps, which provide an estimate of the ground damage radius as a function of the explosion yield and its altitude. This is a simplified approach. It does neglect some of the higher fidelity factors, such as the movement of the source, that sort of thing. But when you're running a large number of stochastic cases, it does give a reasonable estimation of the damage trends and relative sensitivities. The usual curves used are based on nuclear data, the Gladstone and Dolan height of burst maps. But these are based on very small yields that don't necessarily scale very well to larger energies that are involved in asteroid impacts. So for our pair model, we also incorporate some computational fluid dynamics based height of burst maps that were developed by Michael Aftismus. And we interpolate between the Gladstone and Dolan curves on the lower end below 5 megatons and the CFD-based curves for larger yields. And one of the important trends with using these height of burst maps is that for any given energy, there is an optimal burst altitude that's going to give you your maximum damage radius. And where that optimal burst height is and how specific or narrow or broad it is will sort of determine your sensitivities to your breakup. So here we're going to look at a specific example of that. This plot shows the range of burst altitudes that we get from our model for a sort of nominal stony asteroid type entering at 19 kilometers per second and 45-degree angle with a variety of strengths, densities, and diameters. And then we can overlay that with the optimal burst altitude ranges from both the Gladstone and Dolan nuclear curves, which are shown in blue, and the CFD-based curves, which are shown in red. And the ranges here, the dotted lines, represent the altitudes that give damage radii within 10% of the absolute maximum value. So this gives us a sense of where some of the sensitivities are, where the sensitive regions and less sensitive regions are for these different assumptions across different energy regimes. You can see that the nuclear curves have higher, broader optimal altitude ranges, while the simulation-based curves have lower, narrower optimal ranges. And so the modeled altitudes tend to pass through the optimal range of the nuclear curves much sooner, by which I mean smaller energies and higher altitudes than they do for the simulation-based curves. The simulation-based curves tend to stay within the burst altitude range over a larger span of energies. And so now we can look at how that affects our damage estimates. The plot on the right is the same plot we showed before. The plot on the bottom shows affected population estimates for those same entry cases. The blue data shows the damage estimated using the Gladstone and Dolan nuclear curves, and the purple data shows the pair results that interpolate between the nuclear curves and the CFD-based curves. And you can see how the greater overlap of the optimal burst region for the CFD curves produces much higher damage estimates and much broader uncertainty for those larger energies than if we assumed the nuclear curves. Can also see how the overpenetration of the sharper CFD height of burst curve sort of makes the damage fall off faster than it does for the Gladstone and Dolan curves. So even as you're going up in energy, your average damage and your maximum damage can start to fall off as you overpenetrate below that sharper nose of the CFD-based curves. And so this is a more specific look at how that can affect the sort of damage footprints in ways that we don't necessarily expect. So these are some sample ground damage footprints placed over Washington, D.C. just for scale. On the top row, we have some stony type asteroids, and on the bottom, we have some stronger, denser, higher energy iron type. The left is 60 meters, the middle is 200 meters, and the right is 500 meters. And for some of these, you can see it sort of trends as you expect. As you get bigger in size, the damage area gets bigger in size. But for example, in the middle two 200-meter plots, on the top, you have a weaker, lower energy burst producing much larger damage area than the higher energy, lower burst of the iron type asteroid. And also you can see how the different PSI damage levels here, there's the yellow one is the 1 PSI, the orange is 2 PSI, the darker orange is 4 PSI, and the red is 10 PSI. You can see how the trends vary a little bit differently among the cases. So with all of this, the strengthen breakup parameters can be important for assessing specific cases or transitional energy regimes, particularly cases where the strength and breakup factors span or approach the optimal burst altitudes, or for smaller cases where only very low bursts will produce damage. We are continuing to look at developing better methods for getting more specific damage estimates based on the full range of the energy deposition rather than just using an estimated peak altitude, looking at more sensitivities, and looking at transitioning FCM from debris cloud modeling to something that looks at more physics-based spread rates. So that, I will take any questions.
We have plenty of time for questions if there are any questions.
Hi, Jan Osborg with Rand. So you said you used the Gladstone Dolan for one approach, and then for the other one, you kind of mixed the Gladstone Dolan with the CFD. How did you balance that for the mixed one?
So for bursts that are below 5 megatons, we use the Gladstone and Dolan nuclear curves. For bursts that are above 250 megatons, we use purely the CFD curves, and in between, we interpolate between the two of those.
Peter.
Quick question for the nuclear curves. Are you looking at just the yield? Are you taking into account that half the energy goes into radiation?
Yeah, so we use the entire initial energy of the asteroid for our burst yields. It sort of helps to balance out some of the effects that are not necessarily represented in the height of burst curves. It is just comparisons tend to produce more reasonable damage estimates when you just use the full energy. Because even though it's losing energy coming down through the atmosphere, that energy is still going into the atmosphere and can contribute to the blast, even though it's getting used up along the way.
Great, thanks.
Anything else? Thank you.